Understanding networks and subnetting. The witty way. This is the TIN network, so by default, it has a subnet mask of 255.0.0.0, or more easily written in CIDR notation as /8. A /8 informs us that the first 8 bits of the IP address are the network portion. Think of this as the family names like Jones or Smith. These names identify family groups in the same way network IDs identify network groups or IP ranges. The remaining 24 bits are the host bits. Their states, 1 or 0, can be modified in various combinations to represent unique number values. These values combined with the network ID are the IP address. The values these host bits can represent range from 0.0.1 to 255.255.254. They make a host IP unique within a network. With such a large combination of numbers, it's easy to make almost 17 million unique values. These computers have been assigned IPs that fall within the range of the TIN network. Collectively, they are the TIN network, and individually, they are identified as 10.0.0.1, 10.64.0.1, 10.128.0.1, and 10.192.0.1. First, I ping host B at 10.64.0.1, followed by host C at 10.128.0.1, then host D at 10.192.0.1. They should all be successful, and they are. The point of this is to ensure that all the hosts have reachability. You should follow along and try it yourself with the Packet Tracer lab provided. Later in the video, you'll see why this matters. This is a simple drawing of the physical layout of the setup. Here is the logical view of Layer 2, all devices on a common shared link. And this is Layer 3 logically. For now, it is not much different than Layer 2. Not considering the negative impacts, like performance, there is no benefit to maintaining such a large network. It makes sense to reduce the size by breaking the large network into smaller ones. This is subnetting. But a new network would need a unique ID, and we only have these network bits that cannot be changed. What we are going to have to do is borrow some bits. The borrowed bits must be consecutive to the ones that currently define the network ID. This means that we must look at the second octet. We will borrow one bit, which should be enough to give us at least more than one unique value that can be used for a network ID. Now let's take a look at the unique combinations we can create with the added bit that we just borrowed from the second octet. With the bit turned off, we now have a value of 10.0. With the bit turned on, we have a value of 10.128. We know that the bit can only represent one of two values, on or off, 0 or 1. So now we have two new unique networks, the 10.0 network and the 10.128. You can see that the 10 network is the top level network, and now there exist two subnets. Let's take a look at the host portions of the network. With one less bit, the number of unique values we can create has been reduced. For the 10.0 network, these values range from 0.0.1 to 127.255.254. This allows for approximately 8 million unique values compared to the 6 million before. For the 10.128 network, the unique values are 128.0.1 through 255.255.254. With the borrowed bit, our CIDR, which represents the number of bits used to represent the network ID value, has changed from 8 to 9. Let's reflect that on our lab. We will inform the computers of their new assignments by modifying the subnet mask. The new subnet mask is 255.128. That is all the bits in the first octet of the subnet mask turned on, plus the borrowed bit, which represents the value 128, in the second octet. Now that the computers have been given their new network assignments, let's test out our connectivity again. Connectivity from host A to host B seems to still work. We try from host A to host C, and it looks like we have a problem. Let's try host D. That one also doesn't work. Let's try from host C to host B. Still no luck. What about from C to D? Previously, all of the computers had layer 3 reachability. What is the issue? The answer is that they are not all in the same network. The computers are still in the same physical network, and logically, at layer 2, they are still in the same link. However, at layer 3, this is what the devices see. I will leave the full explanation for another video, but the simple answer is that the computers know which IPs are within their network group. Same network must mean same link. Different network essentially means no layer 1 or layer 2 reachability to the link the remote device is connected to. That is, from the perspective of the computers. We would like to further split our networks, but as you see, we only have these 9 bits, and they only make 2 unique values. Once again, we will need to borrow a bit. We've borrowed a second bit, now bringing our grand total of bits for the network portion to 10. With both borrowed bits turned off, we again have a value of 10.0. With the rightmost bit turned on, we have a value of 10.64. That one is turned off, and the next one turned on. This gives us a value of 10.128. Lastly, we return to the first bit and turn it back on, giving us a value of 10.192. You can see that with 2 borrowed bits, we are now able to create 4 unique network IDs. The 10 network has now been subnetted into 4 networks: the 10.0 network, the 10.64 network, the 10.128 network, and the 10.192. This table shows the 4 available networks and the ranges that they consist of. Reducing the number of host bits that we have has now reduced the number of unique values we can create within each network to approximately 4 million. The computers need to be made aware of their new assignments again. Recall how we did this in the previous lab. Make the necessary changes and come back to the video to see if you are correct. The new subnet mask is 255.192.0.0. This is the original 8 bits plus the 2 borrowed bits, one that represents 128 and the other that represents 64, together 192. Now you have seen how easy it is to move a device from one network to another by simply modifying the subnet mask. The subnet mask is what makes the computer aware of what portions of its IP belong to its network ID and which portions belong to its individual host ID. This is now what our lab looks like from the computer's perspective.